So I think we're here. So here we are. We've finished running on a desktop. And let's talk about running on a cluster. So what are the differences between running on a desktop machine and running on a cluster? As I mentioned before, one of the first things is it usually requires additional parameters for the batch queue system. And one of the very sort of user-friendly aspects of PyLith is that PyLith knows about several common batch queue systems. So you don't have to know much at all about how to create usually a shell script to run to submit to the batch system. You just need to know what information you need to give to PyLith so that PyLith can create that batch shell and submit it to the queue system. The second important thing is, earlier I said HDF5 output is much faster than the VTK output. There's two types of HDF5 output. There's HDF5. There's two types of data writers in PyLith for HDF5. There's our data writer HDF5, and then there's data writer HDF5 external. And the difference is that when it actually writes out the displacement arrays and so forth, in the external writer, it's writing them out to a separate binary file. And it's using some low-level parallel processing input-output routines to do that. Then, in order to create the HDF5 file, the HDF5 file, the .h5 file, is simply a metadata file that says, here is the binary file that contains the values for my data set. And the advantage of this is that HDF5, because it's similar to a database of arrays, if you have if say one compute node goes down or the cluster crashes in the middle of writing your HDF5 file, basically that whole sort of database, if you would call it that, can become garbled. However, with this other approach, using these external data writers, we're only touching the HDF5 file with one process, and we can actually reassemble the HDF5 file on the fly after all of these external data sets have been written. And so we don't really support that at this point, but it's feasible. But what it does do is, by only writing the HDF5 file using one process, we end up with a much more robust system, and it's much more fail-safe than the regular HDF5 output. And it's also, when you're running on a cluster, you want to take advantage of parallel file systems if they exist. And other things to note are that your standard output and standard error, instead of generally being written to the screen, because you're running through a batch system, they're going to end up in log files or files. So some batch systems will allow you to combine your standard output and standard error into a single file, or you can combine them into separate files. And some batch systems will allow you it'll actually put that log file in your working directory. Others will put it in some temporary directory on the compute node, and then copy that back to your working directory once the job is done. And so in some cases, it's impossible to actually see where you are in the run until the job finishes. In some cases, you can poke around if you can log into those compute nodes and actually find out what's going on. And so I'll show you one way to do that on the cluster here. And it's important to consult your system administrator on MPI parameters. So whoever is administering your cluster may have installed more than one version of MPI. There may be one version that is more optimized or sort of has a better compiler suite for your particular hardware. You want to, some clusters support both a fast communication between processors as well as just normal, that's usually called InfiniBand. The other sort of more common is sort of just the regular gigabit Ethernet. And so if you have InfiniBand, you want to be using it because the interprocessor communication is much faster. And so you get better performance, fewer bottlenecks. If you're going to be running at say a national computing center, you want to make sure you read the Getting Started guides, because there almost certainly there'll be multiple compiler suites. A lot of times the Getting Started guide will indicate sort of what is the preferable one and how to switch in between different compilers, because they usually set things up so that that they make it relatively easy. So environment variables are usually more common now, module commands to switch between different compiler suites and compatible versions of MPI. You also, if you're running a computer center, you want to ask about what file systems are available and which support parallel input-output. Usually they'll say, don't use your working directory or your home directory for large parallel output. Usually there's a specific file system that's set up for your runs, and usually those are wiped clean, sometimes within 24 hours, sometimes a week, sometimes a day, or 2 days, because they're meant to be temporary storage while your job is running or shortly after it's finished, and then they want to clear your stuff off so that someone else can make use of that space. So some hints for running PyLith on a cluster. One of the most common questions that we often get is, how many compute nodes and cores should I use? In general, some hints are if you have n compute nodes and you want to be running n j jobs simultaneously, just divide up your jobs among the compute nodes. In other words, if you want to be running two sort of simulations at once, you wouldn't, or if you have two simulations to run, don't use 2/3 of your cluster to run a job. Run it on, if it'll fit on half, then run 2 jobs simultaneously. And so also be kind to other users. Don't sort of always run on all of the compute nodes. Run on sort of the where it runs, make sure the job will fit, but make sure you don't sort of monopolize the machine too much. Other cases or things to consider is if you're running on a computing center, or even if you have a larger cluster, say in your department, there's probably a queue system with multiple queues. And so you may find that there's, say, a queue for running up to, say, let's just say 56 or 60, let's say 64 cores or processes, and jobs are allowed on that queue to run up to 2 hours, and then there's another queue where you're, say, using up to 128 cores, where you can use a whole day. And so what you want to do is, if your job is only going to take 2 hours and there's a much shorter wait for the queue on which it'll fit, use that queue and only use 64 cores rather than waiting longer to use a queue that takes 128. So you can sort of play the game of where the shortest wait is to maximize basically your scientific throughput to get results in the least amount of time. Make sure you don't overload a compute node. So if you try and throw a really big job on, say, even your desktop or one compute node, you may exceed the amount of memory that's available, and that can cause, on a cluster, the compute node to essentially crash. So you want to make sure that you keep in mind exactly, looking at, based on how much memory your compute nodes have, how it's partitioned among the cores, as well as how many degrees of freedom you have in your job. Just make sure you don't exceed, and so you keep track of how much memory is available. And depending on your system, sometimes you'll get that information in a log file. Sometimes you need to actually, there's some tools you can be running top on each process that's collected in a GUI, and I'll show an example of that for the cluster here. And Also, you don't want to overload the file server, so PyLith is going to, each process with HDF5 output is going to write. So if you are using a system that has just sort of a single global file server with a big RAID, you could overwhelm it if you're running on, say, 1,000 cores. And so most clusters are set up with the right number of sort of a file server for input and output for large jobs that's consistent with sort of how many cores you have. But in some cases, you can end up on a department server that's sort of been strapped together that maybe most other people aren't doing that much input-output, and if you end up doing a lot, you could overwhelm your file server. So some cases there, you actually want to reduce the number of cores you're using so that they don't get hammered by all the traffic over the network. Now, in quasi-static problems, as we discussed in the last session with solvers, memory use and runtime can depend on your solver parameters. So things like the LU, obviously they don't run in parallel, but that uses a lot more memory, and especially like the parallel versions of that using mumps and super LU are going to use a lot more memory than some of the other solvers. In most cases, with the solver parameters we recommend, the memory use is going to be dominated by the sparse matrix. And other things to be aware of is that the different bulk rheologies use different amounts of memory. So when you're judging, how much memory is my simulation going to take, just a simple elastic model doesn't have to store any state variables. It can compute strains and stresses on the fly, whereas a nonlinear model needs to keep around state variables so we can update those state variables and keep track of how much plastic strain or viscous strain there's been. So, if you don't do all of your testing with elastic materials, if you're going to do a large run with more complicated bulk rheology. And also, when you partition your mesh, if you have different rheologies that are using different amount of memory, that's going to cause some memory imbalances. And so you may end up with some processes that are going to use a lot more memory than others. And so you want to make sure when you're actually monitoring your job that you're monitoring the processes that are going to be using the more memory, or at least get a total picture of what's going on rather than just a single process that may be using less memory. Dynamic problems, it's a little less complicated because we don't have the sparse matrix, and so basically you just don't want to overload the compute nodes with using exceeding the amount of memory or exceeding sort of your file system. The other thing to keep in mind is on dynamic problems is the spontaneous rupture. If we have to keep track of the information about the fault constitutive models in the fault, because some of those, like rate and state, have state variables, they can use more memory than prescribed. They will use more memory than prescribed slip, and so sometimes you'll see a significant difference in memory usage between, say, a prescribed slip simulation and a spontaneous rupture simulation. So let's look a little bit at PyLith performance. This is the test case we used in our JGR paper. This is a pretty simple domain. It's just a block, but we put in 3 faults that are intersecting, and this was to sort of stress. So the fact that we have multiple faults means we essentially have multiple saddle points in this problem. So this is a we're going to just solve the static simulation, so it's not going to do a lot of time steps, but it's going to give us an idea of how our preconditioners and solver scale, both in terms of problem size as well as how many iterations to compare the performance of the different preconditioners. So this is the table right out of the paper in terms of for the different preconditioners here in the first column for both a TET mesh and a hex mesh for 3 different problem size, the number of iterations. So some of these iterations are faster than others, so this isn't a complete picture of the performance, but it certainly gives you an idea of the difference in terms of the number of iterations for the different preconditioners. So our additive Schwartz, that's what we used in some of our very small 3D hex 8 type examples. For a TET mesh or hex mesh, for our first problem size, we're using in the order of 140 to 180. Then as we increase the problem size, so I think each of these is about a factor of 2, or I think it's a factor of 2 difference in numbers of degrees of freedom. So you'll see that we go from 180 up to 270 iterations for convergence. These are all using the same tolerance. They're all solving the exact same problem in terms of what the boundary conditions were. Hexate, starts with a lower number, ends up about the same percentage increase. Here's the sure complement with the full combination. You notice we've reduced it considerably, and we see a less increase with problem size. Using the sure upper, you'll see that again, small, modest increase in the number of iterations as the problem size go up, and it's even less for hexate than TET4. Part of this just has to do with how many degrees of freedom and sort of the very unstructured nature of a TET4 mesh compared to a hexate. When we put in the field split with the additive combination, you'll notice that that really does not perform very well. When we go to multiplicative without the custom preconditioner, again, it does not do very well. But we actually, in this case, for these problem settings, which don't quite match up with the Solver 07 settings, I think we have yet to test those Solver 07 settings on this particular example. But you'll see that our field split multiplicative combination with our custom fault preconditioner does extremely well. We have very modest increase in the number of iterations as the problem size goes up. And so this is going to scale very well and give us, as well as it gives us a very good preconditioner. Looking at how this scales in terms with that field split with the algebraic multigrid and custom fault preconditioner, this is looking at what Matt referred to as the weak scaling. And so we have the same, we're basically taking the same size problem, and as we increase the number of processors, we increase the problem size in 1-to-1. And so if we have twice as many processors, we increase the problem size by a factor of 2, and so forth. And so we start out here on just a single processor down here at the left side, and then we went up to, I believe in this case, it was 96 cores. And this is on Lone Star at the Texas Supercomputing Center. And so the different symbols, the square is for hexate, the triangle is for TET4. And so here's the reforming the residual. Notice it's a very small fraction of the runtime. Computing the Jacobian or sparse matrix is bigger. Generally, these are relatively flat, but we do get some variation. This variability is actually due to the fact that we're not using the entire machine. We're just using a very small fraction of the machine. So other jobs, depending on how many other jobs are running and how much communication is going on, they'll actually affect the performance of our job. And so we tend to get, even though overall we have sort of a flat curve here, we do get some sort of fluctuations. In some cases, we would run things multiple times to sort of get a better, see if we could do better. And then this up here is the overall solve. And so we're getting, this is the linear solve. And so you see that part of this is due to this is the total time. And then this right panel is showing the number of iterations. So we do get a modest increase in number of iterations. That's contributing to part of this slope on the left-hand plot. But then there's also parts of the algebraic multigrid preconditioner don't scale as well as other parts. And so this is an area where by looking at our log file and really looking at the events that are going on in more detail, we're able to isolate which parts are scaling well and which parts are not scaling well. Okay, and so let's look at a PETSC log summary and just sort of a little detail to get information about what's going on when we do sort of these larger runs. And so on the left side, I'm extracting a small piece of the PETSC log summary from running the Savage and Prescott benchmark that's discussed in the manual as well as our PyLith paper. And you'll see in this case that 85% of the time is spent in the solve. And so when we look at this from a quasi-static standpoint, optimizing our code really doesn't, there's so much of our code really doesn't contribute to the bottleneck in performance. But our solver settings are going to have a huge effect on how fast we get a result when we run a job. In this case, we're using the field split with a custom preconditioner, and so we get nice results in terms of scaling, and the solve is going pretty fast. And so we'll see when we do some experimentations if the parameters that Matt has come up with in the solver07.cfg file that he talked about last time, combining the sure complement with these other solver settings will allow us to get a faster solve. My feeling is it's going to be very close to what we had with the algebraic multi preconditioner, field split, and custom fault preconditioner. On the right, I'm showing a dynamic rupture simulation. This is a rate and state dynamic rupture simulation benchmark. Notice that there's no solver stage in this case because instead of the PETSC solver, we're using our trivial decoupled solver that works for these explicit time stepping cases with a diagonal Jacobian matrix, which is essentially our lumped mass matrix. In this case, notice that the performance, or where the code is spending its time, is distributed between reform residual and step. And so the step is in this case, includes our solver. The post-step is output. So with our parallel output, we're spending only 5% of the time doing output, and it was quite similar to our Savage and Prescott benchmark. On the right side, we're running, I believe, on the order of 10,000 time steps, whereas on the left, we're doing on the order of maybe 1,000 in that Savage and Prescott. So a reform residual in this case is where we're really hitting the code. And so in terms of optimizing performance for dynamic problems, we are dissecting our reform residual routine very, very closely and thinking about how to restructure that to really maximize performance. And that's actually one of the things we're working on in version 2.0 at the moment, is running benchmark cases like this and looking at where we perform well relative to version 1.9, since we changed so many of the data structures. We actually see that we're using less memory, and so our meshing sort of setup is actually significantly less in our next version. I think that might be my next slide. That's a couple slides. So the other thing to look at for in the log summary is what Matt talked about in the solvers, is looking at events like vec m dot, vec ax plus y, and vec max plus y. So I'm looking at across the number of cores that we used, and one of the things we can pull out of the PETSC log summary is the load and balance. So obviously with one core, it's perfectly balanced in terms of the number of operations and the runtime. And then as you increase the size of your mesh and the number of cores, you tend to, due to boundary conditions and things like that, you tend to not be perfectly balanced. And so we start to get up to about a 30% imbalance on 100 cores. If we look at how many operations, million of floating point operations per second we use, you notice as we go from 1 core to 2 cores, it's almost multiplied by 2. We go up to 4 cores, it's almost multiplied by 2. Whoa, at 6 cores, well, for one thing, we're going from 4 to 6 cores, so that's not a perfect factor of 2. But you'll see that we got just a very slight improvement, not the sort of 50% improvement that we would want. And so here at 6 cores, this is a machine with 12 cores per compute node. That's on Lone Star. we're starting to saturate the memory bandwidth. So we're basically sending as much, we're maximizing the throughput of what we can send between memory and the processor in terms of how many floating point operations we can do. So we end up sort of saturating our system here at 6 cores, going to 12 cores. You see it actually went down a little bit. Our imbalance went a little bit up. And so because we have multiple cores sort of competing for sending information back and forth within the between memory and the processors or cores, our performance decreases a bit. But then, boom, we jump up to using 2 compute nodes instead of just 1, and we get twice the performance that we had with 12 cores. We bump up to using 4 compute nodes or 48 cores, and we get essentially another factor of 2 in performance. And then we go up by another factor of 2, and we don't quite get the same performance. So at this point, now remember this is doing the dot products, so there is interprocessor communication, and so we're probably starting to perhaps, depending on the size of the problem, maybe we're starting to run into communication bottlenecks.
So
in this case,
I'll just point out here that the bottleneck here is not in the amount of communication. It's what we call latency. It's the time to wait for everyone to get the answer. And this wait time is exaggerated by the load imbalance. So you have a lot of load imbalance. So some guys finish early, some guys finish late. All the early guys have to wait all the way until the late guys finish in order to get the answer. So what you see is when you have to do what's called a reduction, where everyone has to talk to everybody, you can see these long wait times, and therefore it wrecks the scaling.
Thanks, Matt. And so you look at these other, like Beck X plus Y, and so here you see that we hit sort of the same type of issues in terms of saturation within a single compute node, but then as we go to more compute nodes, here we're not running into the same issue with the reductions, and so we get nearly a factor of 2 in performance as we go from 48 cores to 96. Beck MAXPY, sort of the similar type issues, only here we run into a similar type of issue with the reductions in communication. So these are the types of, I point this out not necessarily because you're going to want to dissect your log summaries to this extent, but the fact to point out that you're going to saturate your memory bandwidth usually within, say, a third to half the number of cores per processor that you have. So don't expect as you start using more of your cores that you're necessarily going to get that much better runtime. But you will get better runtime if you start using more compute nodes. So, you know, sometimes you may want to, usually you tend to fill up all of the number of cores on a compute node, but you need to sort of realize that you're not going to, that your sort of performance is really going to be sort of based or equivalent if you're using maybe even half the number of cores. And as we continue to improve the code and sort of do some optimizations, you know, in some cases we may be able to squeak out a little more performance. And part of this is going to be as architectures evolve and you start putting lots and lots of cores on compute nodes like you have with a GPU, there will likely be additional optimizations in the parallel processing to make things go a little faster. Your sort of parallel processing paradigms are going to shift a bit. So a few final comments before we start writing in parallel and looking at the batch system is how version 1.9 will differ from version 2.0. So in both cases, we read in the mesh by a single process, and so that's limiting the size of the calculation. With version 1.9, we've been running sort of up to basically PyLith version about 1.7 to 1.9. We've been running dynamic problems with greater than 50 million cells, either hex or tet meshes. You know, those aren't huge problems, but you certainly can do quite a bit of science with those type of problems. Quasi-static problems, it's really the physics that you want to put in, and and it's not so much you really don't hit these 50 million type cell problems because you can do things like coursing the mesh and using unstructured grids, and so you usually don't need the same computational powers you need for the dynamic problems need, because they need the fine resolution to resolve the propagating seismic waves. We have found within PyLith 1.9 in these large dynamic problems that you can get memory imbalances of up to 10 times for large problems with these spontaneous rupture faults. So that's something to be aware of, that as you run the really large problems, the memory imbalances tend to increase. And so I've had to be very careful in setting up some large dynamic runs to make sure that I spread things across enough CPUs so that the maximum memory use on any compute node is not exceeding the amount of memory available. So in some cases, I'm using on some compute nodes, I may be only using 10, 20% of the memory. Others, I'm using 90%. And that is going to change in PyLith 2.0 because Matt has spent a lot of time working on these mesh data structures. And it's essentially, now that he knows how PyLith was laid out, he was in rewriting the data structures to put in things like the multiphysics and so forth. He said, I know how to write the data structures to have all the features we need and make them memory efficient. And so we expect our memory balancing to be very good in PyLith 2.0. Once we get all these parallel bugs fixed, then we'll be testing and verifying that that's true. And so we expect, because of this memory balancing being fixed and the fact that the improved data structures are reducing the amount of memory use, that we're going to be able to run problems, on the order of 100 to several hundred million cells using on the same hardware that we could not run that size of problem on version 1.9. So things are looking up. We're running much larger problems, and then as we go to higher order, that's also going to not increase the number of cells, but it's going to increase the amount of resolution that a given mesh has, and so it will take more memory, but we're also going to be really beating down in terms of being able to scale to much larger problems in terms of the total number of degrees of freedom. So on the cluster, you do have to build from source. A couple years ago, we created this PyLith installer that's just this little tarball that downloads, configures, and builds PyLith as well as all the dependencies. You can select which dependencies are needed, and the installer will do some minimal checks to make sure that those dependencies exist. For example, if on a cluster, you're generally going to tell it, I don't need MPI, don't build the MPI. And so the installer configuration will make sure that it can find the MPI compiler so that it can build things for using MPI. It also ensures that all of the versions and configurations and builds of the dependencies are consistent with what PyLith requires. For example, we want to build HDF5 to run in parallel. We need PETSC configured a certain way, and we need a specific version of PETSC. And there's some of the dependencies where perhaps the latest version we haven't tested yet, and so we're going to use a version that we know works with PyLith and that we've tested against. The other issue I want to point out is the install file bundled with the installer includes instructions for various configurations, like if you want to build on a desktop versus a cluster, a Mac versus a Linux machine. The PyLith installer will work for all of those, but usually some operating systems such as Linux, you're going to be installing things from the package manager that's bundled with the operating system. And so you don't need to build as many things as you do, say, on a Darwin system where the package managers are much more sketchy. And that's all I'm going to say about building from source. Basically, use the installer. If you run into problems, send an email to CIG short. Perhaps in the future we'll have a special sort of session on building from source, and we'll go things in more detail. So now let's run a parallel job on a cluster. So as I mentioned before, PyLith uses Pyre to submit jobs directly to the batch queue system. I'm going to go through the PBS queue system. The user manual contains some information about using the LSF queue system. PBS is one of the most common batch queue systems. It's also known as Torque MAUI on a number of clusters, depending on which version was installed. So what the steps that PyLith takes is that first it performs a minimum validation of the simulation parameters. So before I'm submitting my job to the queue, it'd be nice if PyLith actually checked to make sure that I didn't make a stupid mistake. And it actually does that. It makes sure that, all that sort of initial validation of things like making sure you've provided file names when you need a file name, making sure that the components actually exist and not misspelled. It does those checks before it even submits the job to the batch system. Then it creates the shell script to submit the job and submits the job. And it assumes that you've already set up running jobs on the cluster. So if your particular cluster, if you need to be able to use SSH into the compute nodes, then it will actually, we assume that you already have that set up. So if we're not going to, the PyLith does not check to make sure that it can, if there's any, very customized setup in that submit script to the batch system, it does not do that for you. So you need to do that ahead of time and sort of set things up so that sort of a minimal batch script will work. And I'll show you how to check to see what batch script is created. And so we have a question, can I save the flash movie on my desktop for the recorded sessions? You could do a screen capture, but next week we'll be converting all of these flash movies that are streaming into QuickTime movies that you'll be able to download and play on demand. So a few more slides here. This is what my additional PyLith parameters look like. So the first thing I need to do is tell it that the scheduler is PBS, to use my PBS key system. Then I have my PBS component. I want to tell it the shell that I'm going to want it to use to create the job script for the batch system. And I tell it the same shell that I use in my login shell, so that for example, this parameter here, I want it to copy all my environment variables, such as like my path, so it knows where to find everything when it launches on a compute node. So it's very important that if I send my environment variables, that I'm using the same environment in my batch shell as it is for when I do my login. Then I want information about, say, I want to know when the job is started, when it ends, if it's aborted. And so that's what these parameters here are, the -m. So I have the -m, BEA, and then you put in your email address, and so it's going to send the email to you when the job starts, when it ends, or when it aborts. And this Q sub options is for just what the Q sub command provided by PBS expected. So these are, you can put wherever other Q sub options you want on this line. And then the launch command. And so this is that command that launches the job, and depending on if you're using a specific cluster, or there may be a specific way they want you to start your job. For example, the Lone Star cluster at the Texas Supercomputing Center, they have a special command that runs a script that detects which MPI you're using. It sets a bunch of optimized parameters for that MPI version to try and help maximize the efficiency of your code. And so here, what these settings do is it's going to take the variable number of nodes that I specify on my command line and stick it here. And then this is a specific PBS command, that variable that's created on the PBS batch system, that when the queue system decides where my job's going to run, it's going to say you're going to run on compute node, say 0, 2, and 3, because someone else is using compute node 1, then it's going to stick in the names of those hosts and compute nodes here in a special file, and it tells MPI on which compute nodes to actually run. So just a couple final information about using the queue system before we run a parallel job. So again, we're going to use number of the -- nodes equals, and here we're, instead of the number of cores, this is the total number of processes. And then on the scheduler, we tell, and this varies from scheduler to scheduler, we tell it the number of processes per compute node. And so the total number of processes is the number of compute nodes times this processes per node parameter. So we're going to tell it this on the command line in the -- nodes equals number of processes, and we're going to tell it how many processes per compute node. You better make sure that these add up and you don't have a remainder when you divide the number of processes or the number of processes per compute node, or the batch system is going to complain. And so then the other, you generally, when your job appears in the queue, it's going to appear with a name, and so you can use the -- job.name with the name of the job. And then to give it the log file, use -- job.standardout equals log file with a -- job.standarderror for where the standard error would be written. And so just some final debug launching of parallel jobs. I think, well, let's come back to this. And so I'm going to stop sharing, switch to